audience because we just simply don't have time.
Got it. Okay. So this gentleman here, Jonathan, said his advisor did not sign off on live streaming.
Yes.
So we're gonna cut this, we're gonna move him, switch these two,
Yeah.
and then cut the streaming.
Correct, yes. So if you are not allowed to stream, well, actually, I don't remember Martin sent me regarding you or regarding someone else. But he said it's okay to stream, but not okay to put in digital repository, you know? Are you sure that you are not
The live
okay?
streams are being recorded though, so I don't know how that.
Okay, that's fine.
Okay.
That's fine. So yes, please switch. Is anyone else not allowed to present to the online? Okay, that's good.
Okay, and we haven't seen the Brandon yet.
Brandon should come. He signed up for the first meeting.
Okay, okay, all right.
Thank you so much.
You're welcome.
Yeah, I have a thank you for hosting.
Great, thank you.
You can do.
Sure, no, I appreciate that.
But I will ask everyone again, I will see policy, sign the form for that. Shoot your name and then sign.
Oh, yeah.
Yeah. Thank you first. Thank you very much. Okay. So I think we will still later take some pictures.
Okay, fine.
Time will come.
Okay, great.
Thanks. Did you make any changes to your presentations overnight or since Monday? Okay, then all presentations. Okay, good luck, guys. Thank you very much.
Do they don't need to speak into a mic or anything to get.
Nope, these three squares in the ceiling are microphones and they can pick up anything in the room.
Got it, okay.
You shouldn't need to talk too loud or anything, they're pretty sensitive. So.
Okay, got it, thank you. Okay, guys, so we've got about 10:45, so I think we can go ahead and get started. So my name's Cameron McKenzie. I'm an assistant professor in industrial manufacturing systems engineering. I'm going to be chairing the session on this Boeing Fellows. I assume you guys are all, or the present presenters are all Boeing Fellowship Program, which is a program this year where you guys have been doing research with a faculty member on a topic that is of potentially interest to Boeing. And so we have 5 really good talks from different engineering departments. And so the first one is Kundan Paudel, who's in industrial engineering, has been working with me, and he'll be talking about incorporating supply chain design into the engineering product design phase. Okay, I will keep time for you guys, and so about 15-minute presentation, and I'll try to give you like a 5-minute warning. Are you helping out with that? Great.
I got that.
Okay. Hey.
Yeah, 15 minutes, so I'll give you warning at like 12, so we have a few minutes for questions.
Got it. Okay.
Hey everyone, my name is Susan Boyle, a junior in industrial engineering, and I work with Cameron McKenzie, integrating supply chain design into the engineering design. So design and supply chain are two fundamental factors to product development. So designers design the product, whereas supply chain gets the product from manufacturing all through the customer. So ideally, we want this process to occur concurrently as supply chain costs carry up to 80% of the product's cost. However, design engineers often neglect the fact of supply chain, so this is something that's often neglected. So our approach was to identify about a dozen companies that work to bridge the gap between the design and supply chain. So we basically broke them down to design practices and supply chain practices, and further breaking them down into more broader and specific strategies. The next part of our project was to create a simulation to compare the two design strategies. The first one was a non-integrated one where a design is chosen and then the supply chain is chosen. And the next strategy was the integrated one where where a supply chain is chosen, and based on that, a design is chosen. So our aim was to compare the costs related to these two strategies. So starting off, we're reviewing companies that have done different things to bridge the gap, starting off with design practices. So the first broad practice we have is concurrent design practice. So concurrent engineering is a simultaneous development of a product in its development phase. So the benefits outlined here are in the order of about 30 to 50%. So Boeing 777, when it was developed using the concurrent design strategy where different engineering teams work together to get the aircraft built. The fashion company Julep has designers who not only design the product, but also make sure that supply chain is robust enough to get the design into the products. The next practice we have is design supply chain. So the HP designed all in one center, just so they could make a solid supply chain by sending out more printers for the space that they had. So the different departments work together to get this going. Design for supply chain does have a lot of benefits, but it is something that needs some additional cost in the beginning, but the cost offsets in the long run. The next broad practice we have is to simulate flow during design phase. So simulation provides an easy way of assessing the product development without actually starting the production process. So Nissan, when they developed a road, they use simulation in their supply chain configuration process, as well as Honda, who use simulation to monitor the material flow in their assembly. The next broad practice we have is standardization. So standardization basically is an effort to reduce variation among parts. A bad example of this would be the Airbus A380, which used different CAD system to design it, and when they assembled the part, it was physically not able to assemble. General Motors had a similar scenario where they had about 24 CAD systems, but then they reduced that to a standard system, which encouraged more development in their vehicles. Whirlpool also eliminated parts with minor characteristics, which at the end saved them about $1 billion in materials. Now moving on to specific practices, we have remanufacturing, which is the process of returning a used product to its original specifications. So Caterpillar has their in-house remanufacturing facility where they remanufacture parts so that they don't have to overly depend on their suppliers. So, moving on to the next specific one, we have product postponement, which is a process of postponing a product to the last possible moment. So Dell, a tech company, has built-to-order online stores where customers order their product, and they are then sent to merging centers, which combine the orders and they're sent out to the customers. Mazda North America, when they import parts from Japan, they import as a stock model, but they're only configured once they reach the port of entry. So moving on, now we have the supply chain practices, and the first broad practice we have is to recognize supply chain capabilities and capacities. So the fashion company New Look has a good relationship with suppliers, so they know what the supply chain is capable of doing, and they can work on things that they cannot get going. So they also make their design transparent through communicating within their suppliers. The next broad practice we have is control and coordinate with suppliers. So Boeing, when they developed the 787, they used a tier system. So which meant that they outsourced about 70% of the whole aircraft. So it was important that Boeing had good control over the supply chain. So realizing the weakest link in supply chain, they acquired 2 units of lot so that they have more control over how the products flow. The next broad practice we have is the flow-based supply chain. So Dell has their Dell has a mantra of distribution based on demand, where once the customer orders, they're sent to just-in-time hubs to assemble, and those hubs are then replenished by the suppliers. The next specific practice we have is the diversify location of suppliers and facilities. So fashion companies, New Look and Zara, they have different facilities around the globe, and then they can send out designs to different places, and then depending on the trend and demand, they can decide where to manufacture. The pigment company Merck was affected by the 2011 Japan earthquake, as their only plant in Japan was affected, which affected the whole supply chain. So to counteract that, they then made a new plant in Japan. The last specific practice we have is to create different supply chains for different purposes. So Echo, our shoe company, has two different supply chains, one for main order and one for replenishment. And manufacturing just sends out the product, and then their production centers send it out to the main orders and the replenishment points. So the next part of our project was creating the simulation. So we had two different methods, which was a non-integrated approach, where one chose between three design strategies, and then choose one of the two supply chain strategies. As for the integrated one, one would first choose between two supply chains, and based on that, they would then choose a design for to have the lowest average cost. So our aim was to compare the average cost for each strategy. The cost of design and supply chain both have three levels of uncertainties: high, medium, and low. And as for us to get a probabilities and cost, we used a Monte Carlo simulation, which ran for about 10,000 runs. The three main factors that we researched were the correlation between design and supply chain, whether or not the supply chain cost changed for the different design types. And as for the non-integrated one, we want to see whether or not manufacturers knew the true cost of design before they chose their supply chain. So here we can see the results that we got from our simulation. So the highest difference here we have is when a supply chain does change with the design type, and as for the non-integrated one, the design cost is not known. And here we can see the lowest difference is when the supply chain does not change. Putting our data into a graph, we can see that there's a high percentage of difference when supply chain and design are positively correlated. So wrapping up our project, from the literature review, we can see that successful integration required company-wide commitment, which means that companies need to break down from the traditional side of manufacturing. Careful consideration must also be done for life cycle cost, as this integration, while it has benefits, it has upfront costs. And also factors such as communication, coordination, and control of suppliers are also important in bridging this gap. As we saw from the examples, this is something that might be quite easier in high volume industries such as fashion, tech, and automobiles. And as for the simulation, we saw that there are benefits if the supply chain cost changes for design types, and the design and supply chain are positively correlated. And as for the non-integrated one, design costs, if the design cost remains unknown, when supply chain shows that there are more benefits to it. And that was the project that we've been working on this year. And special thank you to Dr. Cameron McKenzie for that. Thank you very much.
Great, thank you. Any questions?
So I guess I didn't really understand the data. It's like, what are your recommendations from the simulations you ran?
So if we were to look at this table, here we see the high difference you see is when there's supply chain design are correlated, right? So that means, let's say if the design costs were high, then supply chain costs would be likely to be high as well, which is why they're positively correlated. So that so we ran it for all the factors that we have right here. Yep, so the three factors we considered, we consider the correlation for cost, positive one, negative one. We consider the fact that supply chain did change and did not change for number two. So both scenarios, and that's for the non-annual one. We ran a simulation for both the factors, whether or not. So the manufacturer knew actually the true cost, which led us to this numbers, which meant that meant to realize what the highest gap between the two costs would be.
That answer your question?
Yeah.
Other questions? Valid question. So what did you learn the most, or that kind of surprised you the most doing the futures project?
So for me at least, from the results that we had, it lined up with the fact that, integrated the design and supply chain was, would lead to higher benefit. So that thought was proved through this project. But then the other thing would be that a lot of companies, while they do have practices, they were not something that were broadly available. So that didn't quite help us, to formulate a plan on how we should go about, because if we had a company, we could sort of like reference what they did and go about that. So that was sort of like a challenge, but seeing what companies did and doing this research and the simulation, it helped learn a lot.
Yeah, we had talked about this, and so since you mentioned it, so why did we kind of think that maybe there wasn't a large amount of information out there in the public about specific company practices in terms of how they're designing and how they might be integrating supply chain into the design phase?
So, I mean, as we kind of talked about, like, if a company is doing something well, they would not probably want to say it out, saying they were doing X, Y, Z, which is the way to our success. So that was sort of like the tough part in finding examples of.
Right. Okay, good. Any other questions? I think we're about out of time anyway. All right, let's thank you again. Okay, so our next speaker is Tyler Trubisky. Get the whole thing started. Computer engineering. Great, thanks.
All right, so my name is Tyler Trubisky. I'm a sophomore in computer engineering, and the project I was working on this year was concerning securing the Open Thread Internet of Things network. My faculty mentors were Dr. Jan Won and Dr. Akhilesh Tyagi, and then my Boeing company mentors were Douglas Stewart and Jeff Paul.
The mouse and actually
All right, so a little bit of background about the Internet of Things. So Internet of Things references the vast collection of devices that are all connected to the internet. So you can think like Ring doorbells, industrial sensors that monitor gauges and stuff on industrial equipment, along with things like smart forks, which I never heard of until this project started, that I guess track how you eat. And generally these devices are low cost and they have really simple interfaces, which is why they've become so prevalent over the last decade or so. And again, that's a double-edged sword, like we'll talk about, because generally the problem with these devices being so low cost is that they have very little security features included on them. And then the growth of these devices is growing exponentially. I believe in 2020, there were about 40 billion devices, and that number is projected to hit like 60 billion by 2025. So in the past several years, several high-profile attacks have taken place using the Internet of Things. So the most notable would be the Mirai botnet attack that happened in 2016 that essentially crashed the internet on the East Coast for like a day. This attack happened by essentially the hackers accessed a bunch of smart devices like smart TVs and smart fridges, and they took control of these devices by entering default username and passwords that have never been changed. So think like username and passwords that are just admin. And then eventually they got enough of these devices where they did a denial of service attack, which essentially you just send more requests to a website than it can handle. And that ended up causing the internet on much of the East Coast to crash. We also have seen examples of people hacking vehicles like Jeeps and piloting them remotely along with pacemakers. And there was even a case of an entire casino being hacked because one of the thermometers in their aquarium was not properly secured, and that gave a backdoor to the hackers to gain access to the network. So given the massive projected growth of the Internet of Things over the next decade or so, security has never been more important to prevent more attacks like the ones we've discussed. Along with that, Google recently released OpenThread, which is an IoT networking protocol that Boeing sees essentially as the future of the Internet of Things. We'll discuss that more here in a second. So the motivation and goals for our project, Boeing essentially on their next generation of passenger aircrafts sees the Internet of Things devices being part of the key role, but they're also worried about the security vulnerabilities that we've discussed. So what we're thinking, or what Boeing is thinking, I guess, is there's going to be different devices on the planet. You think of the galley, you're going to have to access the fridge, so you would scan some sort of card, and then you'd have access to the fridge. Then you would scan a card, and the mechanics would be able to access the engine or the fuel tank. And other people would be able to access the baggage area. But the problem is you don't want one person having access to all of these places. So controlling the access of different people would eventually end up being the main point of our project. So there's been a good amount of relevant work done concerning IoT security in general. But when you look at OpenThread, it was released in 2019, essentially. So there's been almost no security research done on it at all. The work I did this semester continued on some introductory work done by my research mentors and their graduate students last fall, where they just kind of explored OpenThread and what it does. And so our research process methodology that we used here was first we were going to establish an OpenThread network using several IoT devices. We were then going to use the network to explore some details about OpenThread. Finally, we were going to decide our security architecture, and we were going to implement and test this architecture. So establishing an OpenThread network, we did this using Nordic semiconductor boards. These essentially just act as like nodes in the network, so you can send information to and from them, and they can communicate with each other in the network. OpenThread uses a parent-child relationship, which we're going to get into more in the next couple of slides and what that actually means. But essentially, you can think of it as you're going to have one main node that is the parent, and then as a bunch of children nodes coming off it that communicate with each other using the parent node. So we're going to get into more of that parent-child relationship. So in OpenThread, a node can either be a router or a joiner. So you can think of a router as a parent. So if you look on the diagram here, in the top, you see the hexagon with the two light blue circles coming off of it. The hexagon would be your parent, and the joiners would be the two light blue circles. So to communicate anywhere in the network, those light blue circles would have to first communicate through the parent, and then, which would be the hexagon in this case, and the hexagon would route that communication throughout the network to whatever device it needs to go to. And along with that, you can have nodes that will be upgraded or downgraded based on what the network needs. So let's say a parent doesn't have any children associated with it. That parent can actually move to be a child on a different node. And then OpenThread can also connect to the broader internet using a border router, which comes into play with our security implementation. And essentially, this border router just routes communications and signals from within the OpenThread network to the broader internet, and gets the responses back, and then disseminates that information using the border router. So the next step in our research phase was exploring the features and vulnerabilities of OpenThread. So the major benefit, or security benefit, I guess, was that packets of data sent along the network are encrypted currently using AES 128, which is the industry standard for encryption. So that really ended up, originally we thought that was going to be our focus for this project, but once we figured that out, we determined that there was actually a bigger security risk, which was the use of a shared key to join the network. So really all that any device needs to join the network and have full access to anything is just knowledge of the shared key, which you can just brute force eventually if some sort of bad actor wanted to access it. So that kind of brought up the main issue we're going to be addressing with our research. So with that in mind, we had to decide how we were going to solve for this shared key and how we're also going to assign the access levels that we talked about so that once a device joins the network, it can't just access everything. So like we said, we don't want mechanics having access to the fridge and we don't want flight attendants being able to access the fuel tank. So we looked at a couple of different approaches to implement this model that we were talking about. The first of which was a public key infrastructure, which is kind of explained in the diagram to the left. So essentially you have a certificate authority, which you can kind of think of as like the main issuer of certificates that you're going to check all of your certificates against. So the admin of the network can essentially issue a certificate to a device, sign it with its key from the certificate authority, and then when that device tries to join the network, we're going to send a request with the information provided in that certificate to the server and ensure that the certificates match, and then assign it an access level. Other than that, we're also looking at physically unclonable functions to use, which essentially use small differences in the actual computer architecture to assign a security signature. That's a lot more complicated, but it's probably where we're going to go in the future. And then we looked at a couple of other things that we didn't really dig into. So we decided to start with PKI, simply just because it's the easiest one to implement in a quick amount of time. But there is a major drawback there, which is you need to keep the server with all the certificates on it. Which if you think about all the devices on a single plane alone, that's going to take up a lot of computing space. And if you think about an entire fleet of aircraft, your server size is going to have to be absolutely massive. So in the future, like I mentioned, we hope to go to physically unclonable functions because those you will not need a server for. Those are all just locally contained. So actually implementing it ended up being a lot more complicated than we had originally hoped for. OpenThread ended up being like 10 to 20,000 lines of code, I believe. So kind of digging through all of that to figure out where devices are and what we need to do to add them to the network ended up being a lot more difficult than we thought. But essentially, we finally got our PKI server up using OpenSSL, and then we wrote the functions in to OpenThread to get the devices to check their certificates with the certificate authority when they join. So actually, this is updated since when I submitted this, but we finished our final product, and it's currently in a working form. So when you try and join the network now, you will need to provide a certificate and access level. But more importantly than the results we've done, we've laid the ground for future researchers to replace our PKI implementation with a more lean infrastructure in the future, like the physically unclonable functions that we talked about. That concludes my presentation. So if anyone has any questions.
Great, any questions?
Yeah, so you said at the beginning that like the amount of devices IoT is supposed to like raise exponentially over the next few years. Do you think the interest in security is also rising exponentially, or will there be a mismatch there?
I would say yes, but the common issue with security is the cat and mouse game. Essentially, by the time you know something's wrong and you get a fix implemented for it, bad actors have already figured out the next issue. So, I mean, the interest is definitely growing, but it's probably not at the level it needs to be yet for the amount of devices that we have.
So using Google OpenThread, how much can a company like Boeing do if they wanted to implement security measures, either kind of technically or legally? I mean, how much does Google just allow anybody to kind of manipulate this the way they want if they're?
Yeah, so the entire code for OpenThread is open source, which essentially means the community can contribute to it. So yeah, I'm sure in more commercial settings, if you're gonna use it for profit, they would probably have to contact Google and figure out some sort of deal with it. But for the general user, it's free to kind of download and play around with.
And you showed the diagram of kind of the parent relationship. And at least in your diagram, it didn't look like any children could communicate directly with each other. They always had to go through a parent.
Yeah, so
is that the way it works actually in practice? And then if that's the case, it seems to me like, well, if you focused on, in your case, these hexagons, and kind of that's your linchpin for the
security, that could help a lot.
Yeah, so to communicate with another child, it does have to go through the parent, but like I also mentioned, parents can also become children if they don't have children associated with them.
Okay.
So that brings in the problem with kind of isolating each parent with a certain access level, because within Open Thread, they can dynamically reassess themselves to be a child of a different node. So that's why we had to actually include the access levels individually and the certificates for each device.
Got it. Okay, thanks. Any other questions? If not, let's thank Tyler. Very good presentation. Okay, our third presenter is Stuart Pearson. And Stuart Pearson is from electrical engineering, and he's going to talk about designing a 3D microwave imaging system.
Yeah, so hi guys, my name is Stuart Pearson, and in this project, I work with 3 people. My first mentor was a professor in the electrical and computer engineering department, Mohammed Fayad Al-Qasir. He focuses on non-destructive testing. I also worked with one of his PhD students, Matthew Dvorsky, studying electrical engineering, more specifically microwave engineering. And it was also done in collaboration with the Boeing employee, Viral Patel. So yeah, I've been working on this project for the last 2 semesters, and I'd like to take a moment to share what I have learned and what I have done so far with you guys. So before we dive into some of the more technical aspects of my project, I'd like to talk about something I think that we're all familiar with, and that is X-rays. So X-rays are an electromagnetic wave that allow doctors to image cracks or breaks in bones, like that person's arm on the right. But what if we wanted to have some other imaging application, for instance, like scanning the structural supports of a bridge for certain irregularities that might foretell a future collapse, or the precursors to corrosion under the paint of an airplane wing, which might forewarn future structural insecurity, or even stuff like water under the surface soil of Mars. So how could some of these applications be fitted? Well, that answer lies in microwave engineering and microwave imaging. So if we look at the electromagnetic spectrum, we can see that near the top, X-rays have a wavelength on the order of nanometers, whereas kind of near the middle there, microwaves have a wavelength on the order of centimeters and centimeters. And this apparent difference in wavelength allows for different interactions between different materials, and thus we can use microwaves to image different things than X-rays. But before we can understand the basic strategy for microwave imaging, we have to know a little bit about electromagnetic waves in general. So on the left, that red wave represents an electromagnetic wave, and it can be characterized by 2 main qualities, which are magnitude and phase. And magnitude is the difference between the height of the wave and 0 at any given point in time, and phase is the relative position of the wave in time. And so microwave imaging commonly uses something called like a wave inversion. And so we also need to understand what a wave inversion is. And so for one wave to be the inversion of another wave, its magnitude at the same point in time has to be the same as the original wave. And the phase has to be different by 180 degrees. And in essence, this means that the inverted wave should be a mirror image of the regular wave. So we can see here that that blue wave is the mirror image of the red wave, and thus that is what a wave inversion looks like. So if we look over to the right side, we can see a diagram of outlining basic microwave imaging strategy. And so those like V-looking things represent antennas. And so in this case, we have 3 transmitters, the 3 bottom ones, and 1 receiver at the top. So each transmitter emits a microwave that travels towards the target of interest, which we want to scan. And that microwave bounces off the target and is received at the receiver. Now, when that microwave contacts the target, the magnitude and phase of that wave are changed by the target. So that when that wave is received at the receiver, we can do some math depending on the magnitude and phase change in order to create a 3D image of the object we were scanning. Now, something else important to note is that for that map to occur, we need to know from which transmitter each wave was emitted from. And so to do that, we use the things to the left of the antennas called modulators. And in this specific instance, a modulator is able to invert the wave outgoing from a transmitter. And that wave inversion is represented in this case by a -1, where a normally emitted wave is represented by a 1. So because we can control the modulators, we can control at what point in time we want to invert a wave. And if we invert waves at different times relative to each other, at the receiving end, we can distinguish from which transmitter each wave was emitted from, and hence do the math to create the 3D image. So here we have actually the precursor that led to my project, and it's kind of like a nice physical manifestation to look at. So on the left side, we have those 2 transmitters and 1 receiver, and they were moved over the top of that foam block. And on that foam block, there's that X. That X is actually made out of copper tape. And it's important to note that from the point of view of a microwave, that foam block might as well be air, like you can't see it. And this is like kind of the same how with X-rays, the X-ray can see the bone, but they can't see like skin. And so those 2 transmitters and receiver were slowly moved over the top of that foam block so they could collect the sufficient amount of data, which was sending those microwaves back and forth, to create the image you see on the right, which is actually that copper tape. Now, my mentor had a thought that instead of just using those 2 transmitters and 1 receiver and 3 modulators, if we instead had a full array of multiple antennas, we'd be able to gather sufficient data like a lot more quickly. And essentially, similar to how a video camera is able to record video live in real time, if we had that large array, we could have a real-time microwave imaging system. And so that's where I came into this project last fall. I was paired up with my mentors and given the prompt to design, develop, and test a code-modulated multiple input, multiple output microwave imaging array. And this would build off my mentor's previous project, which we just looked at, by constructing a full array of modulators and antennas in order to have the advantages of speed, ease of use, and real-time imaging, which would mean that we don't have to have that strict scanning path and apparatus to collect data. Now, in order to physically realize this new array of modulators, a previous modulator design would have to be changed just a little bit. And so that's where I specifically came in. At the beginning of my project, I was given this 3D model and was told to physically implement it. And so essentially, I would have to design a circuit board that houses this modulator and is able to emit microwaves. And for a bit more context on the modulator itself, if you look at that figure to the right, we give the input signal at pin 1. That signal travels up to the modulator. And depending on the power and voltage we apply at pin 2 or pin 3, the output wave will either be normal or it will be inverted. And so this shows the process of me physically constructing, or not in this case, not physically yet. These are the final renders of the printed circuit board, or PCB, that I made in order to house this modulator and all the other components necessary for the circuit to work. And on the left, you can see the finished product, which was ready for testing. It is the PCB that we received from the manufacturer, which I designed along with all the other components soldered on and ready for testing. And so inside the red box to the right is a zoomed in version of the red box to the left. And that just shows the modulator up close for a little bit more context. So if we look at the picture to the left, we give an input at that gold port that travels up the board and into the modulator. And depending on how we're powering pins 2 or pin 3, again, the wave will either be emitted normally or it will be emitted invertedly. And that wave travels through the gray taper area and out into space towards the target for towards the target to be scanned. And also, it's kind of worth mentioning that I really glossed over this entire PCB design stage. And that's because it's not necessarily to understand the design process fully to understand this project, but just note, especially the software design of my printed circuit board took like the entirety of first semester. And it was a lot of work that I wouldn't have been able to do without a lot of help from my mentors. But so anyway, we have that final PCB, which we were ready to test. And recall that the point of running this test was to ensure that this new modulator design was accurately able to invert a wave. And for, as I said before, for a wave to be inverted, it has to have the same magnitude as the original wave and a phase change of 180 degrees. And so in order to measure if this modulator was inverting waves correctly, we use a device called a vector network analyzer, or VNA for short. And with that, you are able to connect your circuit board to the VNA and measure magnitude and phase. So on the left, we have a diagram of two waves. The blue line represents the wave emitted normally from the board, and the orange line represents the wave emitted invertedly. So if we take the difference between those two waves, we should see a difference of 180 degrees. And indeed, if we look at the figure to the right, we can see that that difference is almost exactly the 180 degrees we want to see. And in a similar fashion, we also had to measure the magnitude. And so here the blue line represents the magnitude of the normal wave again, and the orange line, the magnitude of the inverted wave. And because the magnitude should be the same in each case, if we take the difference between those two waves, we should see a value of 0. And indeed, on the figure to the right again, we see a value that is just about 0. So taking these two measurements leads me to this point in time, I guess, giving this presentation to you guys. So so far, I have built and tested this new modulator design and shown that it works as we intended it. And so the next step or future steps in our project would be to build another PCB with a full array of modulators so that we can test that and hopefully have that camera system or camera-like system that we'd be able to do real-time 3D microwave imaging with. So that would be the next step in the project. So finally, I'd like to thank you guys for listening and thank the Iowa State College of Engineering and Boeing for putting this Boeing Fellows program together, and my mentors for all the help they've given me. Now I understand we have some time for questions if you have them.
Great, thank you. Any questions?
I guess you talked about when you could have a microwave coming in and it would go through the foam as if it didn't see it and could reflect off the copper tape. What's the kind of criteria for whether or not you can go through the foam or you can't go through the copper? Is it like a density factor?
So I don't know all the details in inside that whole subject, I guess. But in this case, I think it has to do with conductivity. So like the copper tape is able to conduct and reflect versus foam is not, or foam has very similar like conductivity to air. So I don't know if that is 100% right, and I don't know enough about microwave engineering to speak fully towards that, but that is something that I think is like qualifier for that.
Thank you. I'm kind of curious in terms of the kind of process of building it. So did you have to like make a lot of different modulators, or did you make one and then have to kind of fine tune it so you would actually get it to invert correctly? I mean, how much of that, or was it basically once you had the software done, then you could basically build it and it worked out?
Yeah, so the new modulator that was supposed to work in the full array or designed to work in the full array was designed like before I came to the project. So I guess like my job was essentially to like physically construct that. And so that's where like this portion I kind of glossed over. I used a software called Altium Designer, which allows you to design printed circuit boards. And so basically, I had to design the modulator itself in Altium based on the 3D model that I was given and some certain other characteristics, and then like design files so that it could be physically constructed.
Mhm.
And that is like shown here.
And like when you physically constructed it and you kind of ran the test, like, what did it work exactly how you showed, or is that the result of fine tuning the physical construction multiple times until you got it to actually work correctly?
Yeah, so actually it was kind of surprising that pretty much everything worked almost in the first go, which my mentor was surprised and almost a little sad because normally you learn a lot from having to troubleshoot stuff. But there were a couple of tweaks that we made as far as having to add resistors in like a couple of spots, but for the most part, everything worked pretty much on the first try.
And how big is these,
So this board that you're seeing on the left, I believe is 2 inches by 2.5 inches.
okay,
To give some like scale perspective.
okay. Good, any other questions? All right, let's take Stuart. Brandon is not here, correct? Who's named Brandon? Does anyone want to pretend that they are Brandon and give his presentation?
There should be a video in his folder.
Are we supposed to just play his video then?
Yeah.
Or if he's not here?
In the previous session, that's what we did
That's
when
what we did.
he wasn't here.
Okay, I guess we'll do that. Does anyone want to stand up here and like pretend like they're talking? Let's say with the video.
Hi, my name is Brian Serby. I'm a third-year student here at Icing from aerospace engineering. My faculty mentor for this project is Dr. Hill, and I want to thank him for helping me in writing my project. Today, I'll be talking about experimental studies on aircraft icing, pivot, and anti-de-icing techniques. To begin, I'm going to talk a little bit about the significance of ice buildup on aircraft and why it's so important to stop this from happening. So when ice accumulates on the surface of a wing or propeller, it disrupts the flow of air, leading to an increase in drag and a reduction in flow. Almost 10% of all fatal crashes are caused by ice accumulation, which is why it's really important to try and find effective techniques to prevent this from happening. There are 2 different ways to mitigate ice buildup. One is called anti-icing, which is typically coating or fluid applied to the aircraft before takeoff. And this essentially tries to stop ice from forming in the first place. The second technique is called de-icing, and this happens after ice has already built up on the aircraft. This can also be fluid sprayed on the aircraft, but there are a few other techniques that are more common. One is shown in the image, and it's called a loop, and basically the little pocket that you see fill up with air really quickly, causing the ice to build up. There are 2 main types of icing conditions. The first is glaze ice, also called clear ice, and this forms around 23 degrees Fahrenheit. This type of icing is usually more dangerous because it doesn't always freeze immediately on contact, and the surface can essentially run back and freeze later and unpredictable. The second is rime ice, and this will begin around 5 degrees Fahrenheit. These water droplets will form immediately on impact, and as you can see in the image, there isn't a lot of run back, and all the particle rings can leave the surface. So for this project, I really wanted to get hands-on experience working on an aerospace project. I've always been really interested with wind tunnels, and it's really cool to see all the different tests and data you can collect from the tunnels. I also wanted to learn from these different measurement techniques and apply what I've learned in the classroom to a real-world problem with aircraft ice. So this diagram shows how the experiment was set up. You can see the propeller blade there in the middle of the wind tunnel, and those typical water droplets going toward the propeller from left to right across the screen. For this test, the temperature of 23 degrees Fahrenheit was chosen, or -5 degrees Celsius, and this was used to produce the glaze icing conditions that I mentioned earlier. Also, the revolution from many other propellers was held constant at 4,200 RPM. So for this experiment, the power consumption, running order, powering the propeller, and the thrust meter, as you can see in the orange line at the top, the RPMs remain relatively constant at around 4,200 RPMs. The light blue line in the middle shows power consumption As I begin to build on the blade and blade become a little heavier, you can see the power increases very, very rapidly. Where you see the sharp decreases, that is when ice sheds from the blade and essentially just flies off the blade. And this process keeps repeating itself for the entire test. The dark blue line at the bottom of the image shows the rest of the blade. You can see that it lines up very closely with the power consumption, and the ice begins to build up one, the thrust slowly decreases. So once the testing is over, 3D scans of the blade were taken to show the ice on the surface. You can see from the two figures on the right that more ice has accumulated towards the end of the blade. This is due to the centrifugal force of the blade. So basically, when the water droplets hit the surface, they are pulled away from the center of the blade, where they then eventually freeze. In the top left, you see the time-lapse video of the ice accumulation, where you can see the ice shedding off of the blade. About every 60 seconds, you can see the big chunks of ice flying off of the blade. So the first experiment was done without any anti-icing or de-icing. This next experiment that I'll talk about uses a few different anti-icing surfaces to see which one performs the best. So for this test, the model aircraft engine was used, and replacing the wind tunnel with very similar conditions that were used on the first test. The first blade is the baseline blade with no blade applied to it, and this is what was used to compare the other results. The next blade is the black blade that you can see, and this is a blade made out of a little bit of softer material, and the last blade is covered in a super hydrophobic coating, which basically tries to repel the water droplets from sticking to the blade. In the time-lapse video, you can see that the softer blade actually performs the best and sheds the ice most often. The baseline blade and the super hydrophobic blade perform pretty similar to each other. Both of them have a good amount of ice buildup on the leading edge. However, there's a little bit more buildup of ice on the backside of the baseline blade. This is because when the ice tries to run off, it can easily do that on a super hydrophobic surface, where with the baseline blade, it can just freeze on the surface. So the next step to this project would be to continue looking at different anti-icing and de-icing techniques and how they affect ice buildup. We could need to continue looking at airfoils or winds and see how they're affected by various icing conditions. I also really enjoy working with 3D imaging technology, and I think it's important because it really provides a basic understanding of how ice accumulates on aircraft. And I think it'd be cool to continue working with this type of equipment. So that concludes my presentation, and I want to thank some people for helping me along the way. Thanks to Dr. Haiyan Hu, Yuan Han, and Minchuan Tian for helping and guiding me in the lab and allowing me to work alongside them. I also want to thank the Boeing Fellowship Program and Dr. Elizabeth Simani for giving me the opportunity to work on this project. And lastly, I want to thank Dr. Hill and Michael Moore for being great mentors and helping me every step along the way. Thank you all very much for listening, and I hope you have a great day. Thanks.
Hey, thanks, Brandon. A little bit more virtual.
We have a few minutes if you just wanna,
I'm sorry, what?
yeah, I said, I think we have a few minutes if you wanna take a little break, if.
I mean, I think we only have one more presentation, so I think we can just. Okay. I would just say let's just go ahead. Why don't you go pull yours up, and just to make sure, because we have to cut the Zoom link, I don't know, you don't know if I should just exit out of Zoom, which I can, but is there like a student helper out here as well, or?
Yeah, I'm not sure where he's at right now.
Okay, well, I'll spend a few minutes trying to see if.
It's the.
Okay. Zoom session here. Sounds good.